factor analysis. My name is James Katende from the Department of Mathematics. I think there are still people joining in, but they'll probably catch up with us on the way. So I'll just share my slides so that we can get started. Okay, in a minute. So kindly confirm that you can see my screen.
You can see your screen, Dr. Ali.
I can see your screen.
Okay, that's good. Putting it in full screen, then we can start. Okay, now it should be visible on your side. So this is today's talk on exploratory factor analysis, and we shall do some demonstration using R. So I'll try to make it as simple as possible. I will not go into too much of a mathematical detail. I think we can arrange for a future talk where we cover more of the mathematical detail. Now, should be able to take the questions after the first part of the presentation. So the first part will be the slides, and the second part will be the demonstration in R. And we can take some questions before the demonstration. Yes, sir. One way is to put your questions in the chat so that we can look at them after the first part. Or if you feel you wish to ask while I'm presenting, you could do that as well so that it's interactive. Okay, so I'll go ahead. So or if you feel you wish to ask during exploratory factor analysis, basically is a technique that works on the assumption that there are some measurements that cannot, or other factors that are not directly observable, but they can be measured indirectly through some observed measurements. And that's the basic idea. It's quite an old technique started by Carl Pearson back in 1904. And this is just repeating what it says. You pick a large number of variables and try to group them into smaller number of variables. So the smaller number of variables are the hidden or the latent variables that cannot be observed directly. And this simply repeats the same thing. The factor is not observable directly. Again, that's repeating the same thing. You find the smallest number of factors that can explain. If you have several variables, you find the smallest number among those several variables that can be explained by a factor. We shall see some examples to make this clearer. Like I said, if there's anything you need clarified, you could ask as well. So we'll illustrate this first with a simple example. So here we have some toy data that we can work with. So these are hypothetical grades for students in an MBA class. So they have 3 subjects. There's a finance, marketing, and policy. And we label them Y1, Y2, and Y3 as our variables. So we pick only 5 students. Ideally, this is not a good sample size, but for illustration purposes, we shall use this. So you pick 5 students and collect their marks. So the idea is this: you're able to observe these scores on the different tests. And here the score was between 1 and 10, the lowest 1 and maximum 10. So you want to see if these variables represent fewer factors than the 3 variables that you're seeing. So the finance is definitely a quantitative course, and marketing, policy exams will not be that quantitative. So you expect that you'll end up with 2 factors, and these will be able to explain the grades So our hypothesis, initial hypothesis would be that finance would measure the quantitative ability, marketing and policy would lean towards the verbal ability of the students. So we'll see how that can be extracted. And that's the basic idea behind factor analysis. You have a bunch of variables. Usually there'll be way more than 3. And you also have a lot of measurements from different people or objects. And then you try to group the variables into factors. But this is just a small example. We'll work with a bigger one. So the model works like this. It assumes these variables can be are linearly related to the factors. Here in our example, we assume that there are only 2 factors. So the model would look something like this. And if you pick each variable, you have what is contributed by the factors, and then there's the error term. So this means the linear relationship is not perfect. There are some errors that are being accounted for. So we label the factors F1 and F2. We named them verbal and quantitative ability. And let's see how they'll be extracted. So these coefficients of the factors are called the loadings. And those are going to be quite important. So if, for instance, the first factor is quantitative ability, we expect the scores on finance to have a higher loading on F1, but a lower loading on the verbal factor. Yeah, Y2 and Y3, because they represent policy and marketing, we expect them to have a higher score on the verbal factor if our assumption is correct. So these factor loadings are quite important. Okay, so so this is basically repeating what we have said. We expect the finance to be highly positive correlated with the first factor, which we claim is a quantitative ability, and the other 2, marketing and policy, should be positively correlated. So this should not actually be 0, but close to 0. But 0 here simply means that the connection is not very strong. So one would wonder, the model looks like a linear model, and why can't you just use the ordinary linear regression? The answer is it's not possible because these factors are not observable. So you can't apply the traditional linear regression model. So there are some assumptions on the model, and we assume that the error terms are independent and have a mean of 0 and a variance. Each of them have a different variance, sigma I, for each of the variables. And also we make the assumption that the factors are independent of each other and also independent of the error terms. They have variance of 1 and mean of 0. So with these assumptions, we're able to split the variance of a given variable into 2 parts. There's the part that is contributed by the factors, the communality, and the specific variance that is contributed by the variable itself. So these models yield this. So this also tells us how good this communality tells us how well the model is represented. This is just repeating what I've said. The communality is what is explained by the factors, and the specific variance is not accounted for by the factors and is attributed to the variable itself. So after running some models, this is what you end up with. First of all, we look at some correlations. So you can see finance is poorly correlated to marketing and policy, but marketing and policy have a high correlation. They're highly correlated. It's about 0.98. If you look at the correlation, but finance is poorly correlated to the 2. So that suggests that they may represent different factors. And when you run the factor analysis on this, you can see the output here. So this represents a first factor. Sometimes they will not be ordered as you have put them in the model because there are some rotations that happen during the analysis, and then they may not be exactly as you named them in the model. So here, if we look at the results, we can see the marketing and policy, they score very highly on the first factor. So we would assume that this first factor represents the verbal ability of the students, and finance scores fairly highly on the second factor. So MR1 and MR2 are just the factors, and that's the result. So how good is this? You can check the first factor. We can check represents about 65% or 66% of the variance. And the second factor represents about 21%. It accounts for 21% of the variance. And cumulatively, they account for about 87% of the variation, which is a reasonable model for us. Looks like good result. So we can now conclude that finance is not a final conclusion. This is something that you'd want to do some confirmatory factor analysis later. But exploratory factor analysis kind of does a first part to unravel the relationships. Then you can do the confirmatory factor analysis. We shall not look at confirmatory factor analysis today. We'll just focus on the exploratory factor analysis. So as we have seen, the solution we got here seems to support our expectations. But there's one thing we can point out, that the factor loadings are not unique, since it's possible to rotate the data and obtain new factor loadings, but you don't lose the underlying structure in the data. The new factor loadings don't affect the underlying structure. Basically, the distances between the data points remain the same. So it doesn't affect the correlation matrix. So, so sometimes it is necessary to do some rotations so that interpretation is easier. In this first case, the interpretation was easy, straight from the initial model. So we didn't do any rotations, and probably any rotations would not have made a big difference. So here we'll quickly run through a couple of steps that you would consider in factor analysis. So one is which variables should be included. And generally, you should get more variables than you actually need, because it's better to have some redundancy in the model. And each factor you suspect must have several variables included. So the participants should be selected from the population you wish to generalize to. Otherwise, you may not get reliable results. You may have to clean the data, check reliability, correlations, outliers, and if there's any missing data. We shall not handle replacement of missing data in this case, but there are ways of imputing data. I'm not too good at that, so we will not handle missing data problems. So you could run some tests to check if the exploratory factor analysis is the appropriate model. And we have the KMO and the Bartlett's test of sphericity, which will help us determine whether the model is appropriate. So in running the model, you can either use the principal components or the common factor analysis. The common factor analysis splits the variance into the communality and the specific variance, and the principal components method does not do that, but they both give you an indication of how many factors to include in your model. So you can also use other methods like principal axis and maximum likelihood to determine the number of factors. These are usually done directly in the program. That's why I'm not going into the details. Some of them will be covered in the R demonstration. There are also some other empirical techniques to check how many factors should be retained. And there's parallel analysis, which does some simulation and works with some averages and compares those to the actual data and picks only, there's also the minimum average partials and the visual scree. The scree plot simply plots the variances. And then from the scree plot, you should be able to see what the model looks like, or what, get an idea of how many factors are should be retained. So we mentioned factor rotation before, that it may be necessary for easier interpretation. And there's the orthogonal, which retains the orthogonality between the axes. Orthogonality simply means, is a big word for perpendicular. Oblique means the angles between the axes will not necessarily be, will not be right angles. So we also mentioned the two major models, the principal components analysis approach and the common factor analysis approach. We had already said that the EFA will split the variance into two parts, but the overriding criteria usually will be interpretability and the theoretical relevance. So most of the time, it's really important to work with someone in the subject, an expert in the subject, to be able to work out the theoretical relevance of the results. Sometimes they may not make sense, or someone in the subject has some experience about how the variables work. So this theoretical relevance requires a subject expert sometimes to help with the interpretation. So for factor extraction, we can use this parallel analysis and minimum average partials. There are other techniques, but these two are good for the following reasons. One, will tend to over-extract, that is the parallel analysis, and the minimum average partials seem to under-extract. And that can give you a good idea of where you stand. Once you get the determined number of factors to extract or retain, you can use some other techniques to compare the model with a different number of factors. We shall see how that works. And after you've done this, you can also use a scree plot again to check. We'll see an example of a scree plot during the demonstration. We already mentioned rotation. So rotation makes the factors easier to interpret because the initial extraction methods simply focus on the covariance among the measured variables, but not interpretability. So when you rotate the axis, you make it easier to do the interpretation. So again, the rotation for the initial extraction methods still accounts for the same proportion of the variance, but it's reassigned. So it's usually important to specify that rotation was used, or which rotation was used during the analysis, because the rotation affects the distribution of the variance. So we can check the model fits using a number of tests. So there's a chi-squared test. These are absolute fit models, so it works, tells you whether your model is actually okay, not in comparison with any other model. The chi-squared test is not very useful for large data sets, because it depends on the sample size, and it will not give an non-significant result, which is what we expect. So this may not be very good for large data sets. The Tucker-Lewis index is usually considered a good fit if its value is more than 0.9. It goes up to a maximum of 0.1, a maximum of 1. And usually a value of more than 0.9 or just around 0.9 would be considered good. Then there's the root mean square error of approximation. That would be good if it's really small, preferably less than 0.05. Then you can compare models using this Bayesian information index, and a lower value for a model means that your model is a better model. So we are going to apply this to this big 5 inventory dataset, which is available in the psych package. It's package, not passage. That's a typing error in R. So this big 5 inventory is basically measures some 5 personality traits. This was a theoretical model. So the traits were named as extraversion, agreeableness, openness, conscientiousness, and neuroticism. And data was collected over 2,800 subjects, and each of the factors had 5 questions in the research. So there are a lot of people who have studied this personality traits, and there's plenty of material out there. So one of the outputs of the analysis usually is the path diagram. I don't know how this didn't come out very well, but you see these are the variables. They are labeled according to the traits because we have like A is for agreeableness, E is for extraversion, O is for openness, C is for conscientiousness, and N is for neuroticism. So each of them had 5 questions. Like you can see A1, there must be an F5 somewhere in there. A1 goes up to F5. So this is the first extraction without any rotation. And you can see it doesn't group the variables very well. What we expect to be under agreeableness is mixed up. Some are related to this first factor, others are related to the last factor. So this may not be easily interpretable, but if you do some rotation and draw the same map, I think this might be better. So now the grouping is a little better. You can see this extraversion seem to be all grouped together in one factor. Neuroticism is sort of in one factor. Conscientiousness, agreeableness, and openness, they all seem to be in one factor. So we ended up with there were 6 factors, but only 5 were picked up. 5 were connected to the different variables. So this is a classical example of factor analysis, and it's very useful. For instance, for human resources, you can determine how to allocate tasks based on personality. For instance, tasks that require a lot of repetition will be suited to people who are conscientious. It's not an exact science here, but it can help people in HR to assign tasks to the appropriate people if they know the personalities of the manpower. So here is a book which has quite an extensive amount of detail. I would recommend this as a book to read for exploratory factor analysis. So I've left out a lot of detail because we are going to run a demonstration in R. And probably some of what I left out is going to become clear as we run the demonstration in R. Are there any questions on what I presented? Am I audible?
Yes, you are.
Yes, you are.
Okay. So you can see there's something in the chat here. Okay, that is great. So I will switch to the R software. The files are available in this folder, Google folder. I think I'll put the folder in the chat. If you wish, you can download the R script. And if you're able to run it, that would be great. But you can also run it later in your own time. So I don't know if you can see the R on your screen.
Yes, you can.
You can see it, yes. That is great. So the first thing we shall do is we redo that small example that we started with. So this first part is just setting up that small example, setting up the different scores in the finance, marketing. Yes?
Okay. Your Word document was covering the R Studios page, but it's now okay.
It's now okay. Okay. So I hope it is clear enough on your end, but if it's not, eventually you will get the, maybe I can enlarge this a bit. You will get, you'll be able to access this R script in the Google Drive. So we set up these two examples and put it in a data frame, which is called grades. Now, unfortunately, I will not be able to explain what is behind the code in R. This would assume that you have some familiarity with R. So I'll just try to explain line by line, but I will not go into details about the R software itself. So we create a data frame. The data frame now contains this same information. Now, this line number 10 is what shows us a data frame. We can actually view it. So if you want to see what is in the data frame, I can add a line here, which allows us to view what is in the file. So if I run this, you'll be able to see the file. So this is the spreadsheet with the file, with the data and the three variables of finance, marketing, and policy. So usually you may want to do some preliminary analysis. There's this psych package that is required for, or you can do it in another way, but the command I want to use is available in this psych package. So I have to load it, then I can go and run this. So this will give us a description of the variables with some descriptive statistics. So it gives us the minimum values, score is 3 in all, maximum is 10 in finance, 9 in marketing, and 8 in policy. We have the skewness and kurtosis. This will tell you whether how symmetrical the data is or how peaked it is for kurtosis. You have all these other variables. So you can quickly run through and see the descriptives of your statistics to see if there's anything amiss. You probably will compare it with what you expect to see. If it is out of order, then you may have to go back to the data and fix it. Now, at the next line, we perform the factor analysis. This is a command that performs the factor analysis. This F8, this is from the psych passage. So Once you run the model, this first one is without rotation. For this one, rotation does not make a big difference. So the second one does some rotation to improve interpretability. But after we have done that, we can access the loadings. The loadings tell us how to get the factors. We already saw that in the demonstration. So these are the loadings. You can see marketing and policy have very high loadings on this first factor. So we will assume that's a factor that covers a verbal or qualitative ability, and finance is separate in the second factor. That seems to suggest that this one measures the quantitative ability. But ideally, you should always have more than one variable, at least 4 or 5 variables per factor for it to be reliable. This was just a simple example to illustrate what happens, but it's not ideal. So the next thing is now we'll work with the big 5 inventory data, which is available in the package. It's available in the package site, so you don't have to load it from anywhere. You just access it from, once you load this library, you'll be able to access the data. So the data itself is called this small b, small f, and small I, but I store it in this variable called BFI data. And I run that. What have I done? So I store it there, then we can view the data, but you see what it's like. So you can see these are the 5 variables that were measuring agreeableness, and these are the scores. I think the scale was from 1 to 6. Then the conscientiousness was measured by these 5. I don't have the questions, I think, but this is easily available. I think you can look it up. The questions that, the actual questions that were represented by this, but they were on a scale from 1 to 6 and so on. So you have all each factor was represented by 5 variables from the theory. And we had some demographic data here, which we don't need. I think I must have removed it from, so the rest just keeps, this is looking at what is in the data. Head simply gives you the first few rows. You can get the variable names using these names. We've already seen them, so I will not run that one. So we pick out the important data. The data must be numerical. So we remove the demographic data, the one for age, education. We don't need it for this analysis. So we only pick the numerical data using this. And this is what we shall work with going forward. So usually when you're doing this analysis, you split, you may want to do confirmatory data factor analysis later. So what you do is you split it into 2 data sets, one for the exploratory part, and then you can do the confirmatory data analysis later. We shall not do the confirmatory data analysis, but I just included this step for clarity. I will run this. So what I'm doing here is splitting the data into 2. And then I will focus on the portion that we shall use for exploratory data analysis. We will not do anything with the portion that that is for confirmatory factor analysis. We can view the first few lines of the data for EFA. So we just pick the first 2 lines, so you can see they are different. Someone is microphone is on. Don't know. Okay. So you can compare the two just to see they're different, but we are more interested in this portion that we shall use for exploratory factor analysis. You may be interested in the number of complete cases because missing data, too much missing data also can be a problem. So this part checks the number of complete cases, and most of our cases are complete. So this true here simply says most of the cases are complete, and the ones that are not complete, about 174. So that's good for us because most of our data is complete. We can display some of the cases with the missing values using this line number 60. So we just pick up some of the cases with missing values. We've picked only two to show. So this first one has a missing value for E3. That's the only missing value it has. This second one has a missing value for A2, and I think that's the only missing value it has. You can check, increase the number of variables you want to check. By increase, instead of 2 here, you can put 5 or 4 if you want to see more than 2. So these missing values can also be visualized, but you have to install, in case you don't have this package installed, you have to install it and load it, and then run this command on the portion of data for confirmatory reduction analysis. Then when you print it out, I think the one I want the plot. So this sort of gives you an idea of how spread out the proportions of missing data in each variable. I think the variables are too many to list here at the bottom. So we have, it only picks on a few to label the axes. Now, also there are too many cases to label this line on this side. So, but the red represents the missing data. So you can see the missing data is not as much as the complete data. When what you see as red represents the missing data. And also, if you look at the proportions of missing data for each variable, they are quite low, not very high. So that's a good thing. This is another way of viewing the missing data again. There's this package called Amelia. You can load it, and then you can draw the map for the missing data. Let me just do this sometimes. Again, this shows you the missing data. Here we have a legend here that will classifies what's missing. This light color looks like white from a distance, indicates the missing, and the ones that are complete are indicated in blue. So you have quite fairly good amount of data to work with. So the correlations normally tell us how good, whether factor analysis would be useful. So if you have the variables, if the variables are correlated, then it means, or at least if some of the variables are correlated, it means factor analysis may be useful. But you don't want the correlation to be too high also. If the correlation is too high, it's a bad thing. We can try to visualize that using these scatter plots. And we also have histograms for each of the variables. I picked this for only 4 variables because there are too many to fit on the screen, but you could check for the others as well. So I have, I picked only 4 variables. I picked them here. The 1st, the 6th, the 11th, and the 16th variable. Those are the only ones indicated in the diagram. So this shows the correlations. Here, the data is not so linear, likely because of this categorical nature of the data. But you can also view the correlations using this other package called QGraph. Once we load it and run this, it uses lines now to represent correlations. The green lines would be the negative, I think, and the red line would show positive correlations, and the thickness shows the strength of the correlation. So these are too many to make sense by just looking, but it's also another way of considering the correlations. So there are some strong correlations in some of the places, like you can see these, the variables for neuroticism, they seem to be quite highly correlated and so on. So that's a good thing. So the other way is just to observe the correlation matrix directly. But a diagram sometimes, especially if you have fewer variables to work with, a diagram would be good. So here we can, another way to view the correlation is to just plot them. Again, there are too many. Let me reduce the, if I do this, I think we'll have a better graph. Yeah, so there are too many, but here they are. Let me run it afresh. This correlation plot allows you to check on the correlation. So you can see now we have a scale. It's a scale that is put on this side. As you go closer to the blue side, it's a positive correlation. Towards the red side, it looks like red to me. We have negative correlation, but when it's a bit pale, the correlation is low. So if you're looking for the high correlations, you look for the darker colors. The darker colors will give you the variables that have high correlations. And that's a good thing for us. Usually we want to, sometimes some insist on correlations of higher than 0.3. That can be subjective. So when you now want to determine the number of factors to extract, you can use the eigenvalues. Now this is a concept in linear algebra. But this basically picks out the variances from the variables. So you pick the correlation matrix, find the eigenvalues, and we can extract the eigenvalues. And this gives us the variance explained by each variable. Then we can draw this on a scree plot. So the next thing is a scree plot. So this will help us determine number of factors to extract. We usually look for at the point where there is a sudden change in slope. So there's a sharp change in slope around here, and we can count all the eigenvalues that are above that. And usually you want to count the eigenvalues that are bigger than 1. So we have 1, 2, 3, 4, 5, 6. So this suggests that the data has about 6 factors to extract. But you realize that the theoretical framework suggested 5, and we can compare the two later on using the, but the comparison using the BIC is not absolute. A lot of input must come from the subject experts to make a final decision. A lot of this is just exploratory in nature, so nothing final. It's more like a guide. Now you can also visualize the eigenvalues differently using this factormine R package and this command that comes after that. This command here now will give you a different way to visualize the eigenvalues, but it gives a percentage of the variation that is explained. So the first eigenvalues explain 19 and followed by 10, 8, 7, and 6. So the first 6 would stop here. And those are what was suggested by the script plot, where there's a sudden change in slope. Or sometimes they call it the elbow. So that was this is if you were to use the PCA method to find the factors. Now we can run the factor analysis model at the next line. If you run the factor analysis model on the correlation matrix, and then get the results of the model, it has a lot of output, so maybe you can try to run through it. So the model also gives scores for each of the variable. So you can give a score based on the model, you can give a score for on each of the variables. And these factors now you can try to figure out. So there are 6 factors. So this H2 here is what measures the communality or the variance explained by the factors. And this U2 is what measures the specific variance that is explained by the variable. We saw this in the model earlier. So we have the communality and the specific variance attributed to the variable. Communality is the variance explained by the factors. So you can try to find the patterns. You look at the factor and look like for instance, MR2, you can try to look at which variables have a high loading on MR2. And then those variables will be influenced by that factor. You do the same for the others. This one is not easy to see, but we'll try to illustrate this using a diagram. Okay. In a minute. So by generating a path diagram, you'll be able to see those relationships better. Which factors influence which variables. So so this next part does that. So when you run this diagram, I'll have to clear this first. So I will run this diagram. So this gives us the path diagram, which tries to connect. But now this factor analysis is just the initial one with no rotation. So you can see that the factors are not very well matched with the variables. Interpretation becomes difficult when that happens. So but when you rotate, I think I seem to have left out the let's add an option here. So we can put in one of the rotation techniques. See what happens. So if you run this now with some rotation, oh, there's a comma missing here. So now the assignment is a little improved, or it should be. Something is not working here. I can't fix it now, but yeah, something has gone wrong there. The rotation is not. Let's try Varimax. So so anyway, that diagram, I think I'm not sure why this is not working. That diagram now shows the relationships between the factors and the variable. Usually after rotating, it should show a better diagram. For some reason, I'm not getting it right here, but I will fix it and share in the what do you call it? In the folder, the Google Drive. So there's earlier on we had the theory itself suggested that there should be 5 factors. So we can compare what the theory suggested and what the script plot, which suggested that there are 6 factors, the eigenvalues that we picked using the script plot, there are only 6. So if we run this 2, then we can extract the BIC values for both, and the lower one, apparently the one for eigenvalues has a much lower BIC, and therefore, according to the theory now, it should be better. But in practice, that is not all you consider. Also, the theoretical framework interpretability must be taken seriously, and experts consulted on that to get the final decision. So, but if you compare the two using this BIC, it shows that the one for the script plot, the one suggested by the script plot, was better. So the other methods to determine how many factors to retain, one of them is this parallel analysis. If you run it, it will suggest that you should pick 6 factors. Let's see what it has printed. I need to move this up. Let's run it again. Oh, this is printing the wrong one. It should be par BFI. I think I'll have to correct that. So you can see when you do the parallel analysis, it seems to suggest 6 factors as well. You can see where there's a sharp change, although here the eigenvalues, some of them are below 1, but where the sharp change occurs is at 6. So it suggests the 6 factors, again, if you run the parallel analysis. But again, this has to be subjected. Then there's another one called MAP. It uses this command VSS, which tries to find the simplest structure. And when you run this, it seems to agree with the theoretical what do you call it? Model. It suggests that it should be 6. So it takes a bit of time to run. So you can see it achieves a minimum at 5 factors. So it suggests that there should be 5 factors. So the two suggest 5 and 6, and those can be tested using the BIC to determine which one is the best to pick. So I think I will stop there. I probably should now take questions if there are any. This technique is transferable to many other fields. Even in marketing, you can use it to gauge customer satisfaction and look at the factors that customers are considering, given some information you collect on them. Say when they come to shop, what are they considering? Are they considering maybe the prices, the arrangement of the items in the in the supermarket and so on, they're quite applicable. If you are in education, it can help you classify abilities, different abilities like verbal and quantitative based on the grades and so on. Are there any questions? I don't know if I'm still audible.
You're audible, actually.
You are.
Yes, it was quite ambitious to try and squeeze all that in 1 hour, but I've tried to do what I could. Are there any questions on the content? So that can be a good or bad sign. Maybe nothing made sense or everything made sense.
Yes, James.
Yes.
Okay. Thank you very much, James. Good morning, everyone. I want to first of all appreciate your engagement in this, and more so your willingness to give a topic, a talk on what you have done. Of course, this goes a long way in establishing our strength in this field, and also establishing our strength in terms of wanting to share knowledge with the rest of us. So perhaps, of course, the entry point for this analysis, as you may have mentioned earlier on, people were supposed to have installed R and other things on there, maybe comps. So perhaps there are those who may feel they didn't catch up just based on where you are supposed maybe to begin from. Maybe they may have missed earlier sessions, but the other sessions, I know, especially on the other packages, you may not have done it publicly, but perhaps it will be prudent for you to think in terms of organizing from the basics, so that the rest of us can be able to follow. That is, in case they missed anything. But this has been a very wonderful talk. Thank you.
Oh, okay, thank you. Yes, it was difficult to. I appreciate the comments. Really grateful for that. We have a course we run with the UNES where we cover this in more detail. There's a 3-day course. You may not cover factor analysis in that course, but there are other techniques that, like linear regression and logistic regression and so on, which are covered in detail. I think the next cohort will be sometime towards the tail end of April. I think the dates will be shared by the UNES. UNES normally handles that. So we might, if there's a link I can give to the registration for, I don't seem to have it here. But it'll probably be shared in the email. If you check, the UNES sent an email some time back. There's a link to the registration for that course run by UNES according to the cost. But if you have any questions that you feel can be answered now, you can ask. And if it's possible to answer it, we can answer, if that will help you understand the information better. Then
perhaps, James, the entire audience may not be accessible to the university mail or so. So the mode of sharing by UNES, okay, as much as it may be in the public domain, but I know it has been sent to our email several times. So as maybe you wait for questions, if you can also access the link and avail to this group, it's better. is also a form of creating public awareness.
Okay, so
And
I'll look it up. I'll get it from my email shortly.
yes, and also insist on UNES specifying the dates, because now we are about to get to the end of March.
Yes, I will talk to them to firm up the dates. There are a few questions in the chat here. There's someone asking if we can organize confirmatory factor analysis soon. Yes, it's possible to do this. We can do this maybe in about 2 weeks. Maybe I can do that in 2 weeks' time. We can organize for another talk on confirmatory factor analysis. Someone asking if we could clarify the difference between the traditional linear model and the factor analysis. The traditional linear model assumes that you have some variables that are observable, but the factor analysis works with the assumption that you have latent variables which you cannot observe, but then they influence the groups of variables. Then, so there's someone talking about the difference between the value of 5 and 6 can be attributed to outliers. Yes, that is possible. Oh, I think the link to the registration for the UNES training has been posted in the chat. Thank you. I was about to look it up in my email. So this talk was not comprehensive. There was quite a lot I had to leave out. So I hope it made some sense under the circumstances. But we'll definitely organize for another talk soon on confirmatory factor analysis. I think that one I will reorganize it to have some more detail. So Mary says the talk was informative. Thank you for the comments. So you can access the data file in the Google Drive. The link that I shared earlier. You can access it and try to run on your own machine later. So if there isn't anything more, I think we can close the meeting. And I wish everyone an excellent day.